we start to learn the spray combustion. Before we go to the detailed spray combustion, spray frame structures, we need to learn what is the more detail about the liquid fuel atomization. Basically, the atomizer or injectors can be divided as two basic category. The one is the so-called pressure atomizing injector, and it is basically operated by the larger pressure, and this liquid pressure itself will push the liquid out of the injector and to produce the so-called spray cone. And the other one is the so-called the trim fluid injector. That means that we use the other fluid to impinge together with the fuel mainly used for the combustion, the liquid fuel. And these two liquid or gas, they will meet together, interact each other, then they will produce the spray breakup then to the many droplets. And the outcome of spray basically can be divided into the two forms. One is the so-called solid spray, the other one is the hollow cone. Solid spray means the spray cone contains all the droplets inside the cone. That means the interior of spray basically composed of the many liquid droplets. But for the hollow cone, actually the droplet distributions around the spray surface. Okay, the interior, the hollow cone may not have too much or too many liquid droplets. Okay, and let's I just give you a simple examples to represent these two kinds of injectors. The left-hand side represents the pressure atomizing injector. This is a typical example for diesel fuel. Usually, diesel fuel requires a very high pressure to push the diesel because the diesel has a higher viscosity. Then it is very hard to atomize it as a spray foam. You need to a high pressure, especially when you use the diesel spray for diesel engine, because inside of diesel engine, the combustion chamber always to push your air to very high pressure. Then you need to higher liquid pressure to push the diesel into the combustion chamber. Then you can see this is a basic mechanism. You can see there is the plunger, and this plunger basically controlled by the spring. Okay, this spring has the some spring force to keep your plunger to close to the supply of liquid. You require a large force to push your spring to have a displacement and to let the fuel flow into the piping, then they will inject out. Okay, you can see this is a fuel supply with high pressure, and those pressure will push your plunger or pistons to move away because this force is large enough to push your spring to the upstream side. Allows the fuel flow in through the injector. Then you will spray coming out. Okay, this is a typical pressure atomizers and requires pressure to push your liquid out of the injector. The other one is a so-called trim fluid. This is a typical example. For example, here the fuel coming from the outer tubing, but they will meet the steam. In this case, you can use the steam or air, and they flow in around the inner tube, and they meet and together before they impinging out through the tip surface of the injector. Actually, they have interactions before they are going out, and these kinds of mixing or interactions will push your droplet, your liquid as the mist coming out. Okay, this is one of the typical trim fluid injector, and they tell you they mix together in the interior of the injector. That means that we call this as some kinds of inner mixing. Later on, I will explain some of the different application for you from the lecture notes. Okay, this is two typical injectors you may run. One is the pressurized injector, the other one is a trim fluid injector. However, when you have a spray coming out based on the typical injector you choose, you may have mainly there's the two category for the spray formation. Here there's the two. The left hand side show you the so-called solid spread. Solid spread represents in the interior of your spray contains so many droplets inside. And you can see if you take a cross section of your spray cone, you will find out around this cross section, then you can find all the position contains a certain amount of droplets. Actually, there's for the whole region of your cross sections contains droplets. Okay, but for the hollow cone means all the droplets will concentrate, accumulate around the periphery of the spray cone. You can see you take cross sections, you will find out there is a ring and contains the droplets lockets. But interior, the center region of a spray cone, they may not have too many droplets. They may have just a few, but there is almost empty for the droplet existence. And this is the initial understanding on the spray injectors and spray formation you may have. Now we go back to our lecture notes, and I need to explain some applications for different kinds of injectors. Okay, now you can see here, this is, let me see this, our slides. 3.1, actually we start for the chapter 3, and the chapter 3 will relate to the spray combustion, and section 3.1 is where we will discuss about the liquid fuel atomization, and those kinds of information you can check with the books from the FACE in 1977 or from the Lefebvre in 1983. And actually, they may have a new edition. You may check it. These two books is a very classical one to give you the more understanding about spray atomization and also combustion. Okay, here I just mentioned there is the two category for injector. One is a pressure atomizing injector. The other one is a trim fluid. And sometimes people will say this as an air assist because there is the trim fluid. That means you have a two fluid, right? One definitely is a fuel because this we use fuel as for the burning, and definitely the primary fluid is the fuel. Then the atomizing fluid, sometimes we use air, sometimes you use a steam because the steam coming from the boiler, right? Because in the power plant you have a lot of steam. Those steam will be flow to the steam turbine to drive the generator to produce the electricity. Then you can bring certain amount of steam to our injectors. And steam has some benefit because steam sometimes has a higher thermal energy, can help the fuel to absorb certain heat for future gasification. Okay, and steam easier to be carried from the boiler generator without applying additional air compressor, something like that. Usually people will use the steam as the assistant fluid for atomization. Okay. Now, typically for pressure atomizing injector can be found in four types. The first one we say the plain orifice. This is the easier one, and you can see there is just a plug. When you change the plug, you move the plug, then you will allow the liquid coming out through the tip of the injector. Depends on the hole distribute on the tip surface of your injector. You can produce a so-called hollow cone. If you have a ring of the small hole on the tip of the injector. Then the spray coming out, they will produce the hollow spray structures. Then the spray cone represent the hollow cone as I explained. Those atomizing droplets will exist in the ring of for the different cross sections. And those application, basically, you can refer to the diesel engine, okay? And the second one, we say the pinto nozzle. Pinto nozzle, you can control the plug inside of the injectors and to produce different kinds of hollow cone or multi-cones. You can see from the figures. If you try, in this case, if you move your pinto or the plug out of the tip of surface of the injector, you will find out all the liquid will coming out from the surrounding of the pinto, then they will produce the hollow cone spray. But you move, if you move the pinto to the left-hand side, that means that you will allow all the liquid contains all the cross section of the tip surface of the injectors, then you will produce the so-called full cone or solid cone spray. Okay, now this is a typical application for a diesel engine or gas turbine engine. The third one, the previous two actually they are almost they mainly controlled by the pressure of the liquid fuel itself. But the third one, not just for the pressure application, we add additional support coming from the swirling motion. Okay, and this is a so-called swirl nozzle. And swirl nozzle means the fuel they will go to, they have some tangential inlets, and those tangential inlets will produce the circulation. Those circulation when a liquid fuel has the circulation inside of the chamber of the injector, then they will move out. Then they will produce a centrifugal force to push your spray to have a radial expansions. Then the spray cone will be expanded. Then they will produce a so-called hollow cone. The flow structure, I will use the one of the figures to let you know the detailed structure later on. And those swirl nozzle basically they tell you the liquid fuel they will be influenced by the pressure itself and also by the swirl motion of the fuel spray. And this typical spray nozzle is widely used for gas turbine. For example, the simplest nozzle, and we will explain it later, and even I will give you some flow structure measurement to let you know the drop size distribution, velocity distribution for given spray co-spray. And the last one we call this is an impinging jet. The jet, there is the jet, the fuel jet, they will divide into two jets, and then two jets are also the liquid fuel itself, but they impinging together. Impinging together represent they have a strong interaction at the impinging point. Okay, and here you can see a liquid jet will separate as the two strings, and then meet together just at the exit plane of the burner and impinge together. And this kinds of mixing or impingement will produce a strong interaction of the liquid droplets, liquid surface, and then they will produce a well mixed spray. Then we call this as a fan spray. Fan spray means that they have a large momentum mixing together, and they will give you the very efficient mixing to produce the very well gasification structures. Then you will go to the more complete combustion, and those kinds of mixing can be finished in a short distance. Therefore, these kinds of fan spray application are usually used for the rocket engines, because we for the rocket engine we need to have a good mixing in a short distance, and this good mixing will promote the overall combustion process more efficiently, and it is good and a benefit for the rocket engines. This I just give you the understanding from the 4 types of typical pressure atomizing injector. Then there is the two type of so-called twin fluid injector. Twin fluid, as I mentioned, one fluid that basically is referred to the fuel itself. The other one is the assist fluid. Sometimes you can use air, sometimes you can use steams. And for example, those kinds of twin fluid injector, basically the idea very similar to the fan spray. They try to bring these two fluids impinging together and to produce large mixtures. Okay, but the impinging point or mixing point will occurs in different position. Then we give a different kinds of name. Now, if, for example, the internal mixings, you can see the fuel will flow around the inner tube, okay, and they are coming out, attached, just meet with the air or steam coming from the outer tube. They mix together inside of the injector. You can see there is the mixing occurs in the interior regions closer to the tip of the injectors. And when they have a good mixing, they will impinge it out and to produce the sprays. You may have a full cone or hollow cone sprays on the exit plane of the injectors. And there is the other type we call this external mixings. We do not have the premixings before they coming out from the exit plane of the injector. The mixing will occur in the outer regions of an injector, and then we call this as external mixing. And for these two applications, there is some difference, different application, because for the case of internal mixings, the mixing occurs in the inner region of the injector. You will see when you apply the steam or fuel with the pressure, there is some kinds of danger. Sometimes you will have a larger pressure of fuel, and will push fuel. This fuel has some kinds of reverse mixings, and to produce some influence on the mixings. But for the external mixings, actually they will not give you the dangers of the fuel finding its way to the air supply. Okay, so you do not have a fuel will moving to the upstream side for the external mixing. This is the have a good advantage. But sometimes people, they will try to bring the internal mixing mixed with the external mixing, try to produce the as large as possible mixing structures. Okay. Now I try to give you some example to illustrate the mixing process or the atomization process. Let's go to the next page. Okay, now this is the first one. I give you the so-called swirling nozzle, the simplex nozzle used for the gas turbine. Okay, you can see this is cross sections of your injectors, and if you look at the horizontal sections of your nozzles, you can see the liquid coming from the has some coming from the tangential inlet. You can see here they will flow in, because this kinds of tangential inlet will give you the liquid fuel will flow around the circle, has a circulation, and this circulation momentums will be pushed out as the fuel coming out, and this circulating motion will give you the centrifugal force. When this centrifugal force pushing out of the injectors, those they will produce, they will enlarge the spray cone, has a radial momentum to give you the more intensity to mix with the air coming out from the outer jet. And here you can see the air you can flow around the center line or from the surrounding, but since the liquid spray has the tangential force and produce the spray will extending the spray cone, and has a strong mixing intensity with the air. Okay, this is a so-called simplex nozzle. And this simplex nozzles, I will give you some example from the basic simulation to the detailed flow structure measurement later on. Then the other example is a fan spray injector, and this illustrated by Lafayette in 1983. You can see air coming in and they will flow from the outer tube, and the fuel coming from the center part, and they will mix together before they coming out of the exit plan of the injector. Then we call this as a this is the inner mixings. Okay, and here also this is inner mixing, but fuel itself, there is the two parts when they inject out through the tip of the fuel injector. You can see they meet together on the tip. Therefore, for the fan spray, you can see there is the first impingement or mixing for fuel itself. Then later on, the fuel will meet with air again, and there is the mixing structures. Fan spray, basically, they combine the two characteristics of pressurized injector and also the trim fluid injectors. The last one, yeah, this is the so-called air brush. Air brush means you use a lot of brush, you use a lot of air, right? Okay, now see, now you can see the fuel coming from here, they flowing along this fuel line, and you can see there is the cross origin represent that they will have a swirling. Okay, they apply the swirling motion into the fluid inside our injector. This is the first one for air and also for fuel. They always have flow circulations. Okay, now fuel coming from this nice and the air coming from the center flowing strings. Then you will see the first mixing positions occur here. Okay, fuel mixed with the air at this location. This location is the inside of the injector. That means that you will have a so-called the inner mixings occur here. Now, after the inner mixings, then the flow coming out, then they mix again with air. Okay, air coming from this line. There is the primary air around the center jet, and the other one, the secondary air, swirling air, they will move from the outer outer flow, and they will have additional mixing in the outer region of the exit plane. Then this is the outer mixing. You bring the intermixing and the outer mixing together, then you will produce mixing structures. Since by the internal mixing and the outer mixings, you require a large amount of air participate. Then we tell this kinds of nozzle as air brush atomizer. Okay, and we just finished some mechanical mechanism for produce the spray, liquid sprays, and basically they will be controlled by pressure itself of the liquid fuel, and also they will have some assistance from the secondary fluid, for example, steam or wood or air. Basically, we call this is a trim fluid atomizer, and you understand how to make the spray as a foam with so many tiny droplets as the main goal for using those kinds of different kinds of atomizer. Then we try to understand if you use those kinds of injectors to produce the atomization. Now we try to understand the mechanism of atomization. Okay, this is a very simple explanation for a liquid jet. In this case, we are dealing with the liquid jet with very small cross sections. Okay, it's a very tiny diameters of your liquid jet coming out, and you can see for the this is the sequence from the figure A, B, C. By increasing of your liquid jet flow velocity. Okay, For the case A, for the figure A, that corresponding to the initial condition, the condition 1, if the exit velocity very small, then that means the velocity of your liquid is very small and almost equal to the surrounding velocity. They do not have a big velocity difference. Then you will not produce the shear force on the liquid jet. Then the aerodynamic resistance do not have an influence on the liquid surface of this jet. And you will find out the liquid jet will extend to a longer distance. Finally, as you remember, I mentioned for a given liquid jet always have some disturbance from different kinds of source, especially from the perturbation from the outer surrounding. Those kinds of perturbations were acting on the surface of liquid jet, produce some kinds of wavy wave motions. Those kinds of wave motion later on the amplitude will be growth to a certain to the certain value, then those kinds of strengths will break your liquid jet as the droplet. Okay, you can see here as the injection below the exit velocity of this liquid jet is very small, and you can see they can continuously retain the the liquid jet shape until certain point they break up as a one point, one droplet like this way. This is a figure A corresponding to the small exit velocity. Then if you increase the higher exit velocity, then you will have a higher aerodynamic resistance. And I'm sorry, this is the pictures for the figure A, and some graphs, systematic diagram for the picture A can be shown right here. They tell you there is some wave motion. Okay, this is a wave motion occurs on a liquid surface. Later on, I will give you some criterions to let you know how much of the wavelength is large enough to break the liquid jet into a droplet, and it will be described by radii descriptions. Later on, I will explain it later. But if you increase the exit velocity higher, then you will the liquid jet will experience the higher aerodynamic resistance. You can see there is the some kinds of wave motions on the liquid jet as described by the figure B, and the corresponding picture shown here. Okay, you can see they will extend longer and with the longer ligaments without detailed breakup structures. Now, if you still increase the higher velocity and the initial turbulence results, I will give you the results. There is some resistance coming from the surface tension, and also they will react with the aerodynamic resistance, then will produce some larger wavelengths, and the diameter of the liquid jet do not change too much. At this point, actually, they do not have a significant breakup behavior occur on the liquid jet. In general, there is the three forces interact each other in the formation of the liquid droplet by from the original liquid jet. Then the first one, actually, they usually have a velocity difference between the liquid jet and also the velocity of the surrounding, right? Then they have a velocity difference. They have a shear force, or we call the aerodynamic resistance, on the surface of a liquid jet. And the second one, there is the so-called surface tension. Try to retain the liquid has the minimal surface energy to retain their stable form. Then the surface tension is one of important force acting against with the aerodynamic resistance. And these two force they acting together, but the wave disturbance, as I mentioned before, those kinds of disturbance will enhance those kinds of interaction. They will produce the very regular or has a certain control frequencies on the liquid droplet breakup. I will tell you from the when we go back to the slides, the detailed discussion on that. And the final part, if you increase the velocity very high, you will find out those kinds of wave motions on the liquid jets do not occur, and they just give you the simple atomization. That means that when you have a liquid jet impinge out, they start to have a breakup process. The atomization is occurs very closer to the injector. This is a typical breakup mechanisms for a liquid jet by increasing the exit velocities continuously from the small velocity and increase. They will tell you the wave motions on the liquid surface for the small velocity is smaller, and you increase the velocity, the velocity of an injector higher, then the wavelengths will become strong, will become larger, and the breakup behavior do not occur for higher exit velocity. Even for the final case, velocity is too high, then the momentum will push all your liquid as so many tiny droplets out of the injector. That means that we go to the atomizing regime. And this is the first part. I try to give you the understanding on the mechanism of a liquid jet. I will go back to our slides to tell you some experimental observation.